Hello everyone. My name is Onur Yuce, and I'm the Creative Manager of Computational Design at New Balance. This year I'm joining the SIGraDi 2020 conference as one of the keynote speakers. I'm really happy that I'll be giving this talk. I'll be very curious to hear about everybody's take on the conference theme, Transformative Design. I look forward to meeting you all online in November.
I'm very happy to be invited to deliver this speech today. So I would like to thank the SIGraDi 2020 organizers for that. I find the conference theme very exciting this year because I think it relates to design a lot. The word transformative refers to some sort of change, and it needs to be a marked change in someone or something, which I find very related to design, right? So in my mind, design is about changing things constantly all the time. So you end up making new things. So when you work in the design realm, then you have to remain transformative, which means that you need to keep changing things. So I find that contradiction pretty interesting. I would like to illustrate this idea with a couple of projects that I worked on. And the first one is from 2012 when I had a chance to visit Santiago, Chile. And the idea in this project was showcasing the potential, the power of digital tools, both in the design realm and the manufacturing realm. And in this case, you would see that you can take a cube, you can slice it in different ways, and you can truncate it in different ways. And then by combining them in different ways, you can build complexity step by step. But at the same time, we were very interested in applying this in computational terms because we had to deal with a sophisticated structure, but at the same time, a sophisticated surfacing system that housed electronics as well as some living organisms in it. And here is how it worked. We picked the spot to put the structure, and then we try to analyze the environment to see what really happens during the day. And that is related to, let's say, how much sunlight enters a space, what the position of the structure is, and what's going to happen with the living organisms that we put inside the structure. So on the structural side, we really targeted to have something that we could digitally manufacture and assemble without using any kind of adhesive or any kind of, let's say, screws and nails and so on and so forth. So the structures that you see here are really friction fit. So that was a super challenging, let's say, application on its own, because what you need to do is you need to cut each and every part in really, really tight tolerances, but at the same time, make sure that they fit to each other, right? If it is too small, it wouldn't fit. If it is too large, it would just be loose and not hold the structures together. And on the living organism side, what we did is we put mushroom in those pockets. And then the amount of opening in each and every pocket would change depending on the location of the pocket on the structure, right? And then eventually we wanted this to be an interactive sculpture as well, right? So then you would see some LED lights in the structure, and people would tweet some colors to these pockets, and then the mushrooms would tweet back their moisture levels depending on the the humidity level that they're at. So all in all, this was a very interesting learning process for the students who attended this workshop to build the structure, right? So it was a workshop, this was designed, but at the same time, we were iterating and reiterating the design as we were building it. So in a way, the design was evolving and transforming over time as we were working on it, right? So we learned a lot, both in the design process, but also during the manufacturing process. We had to reflect our learning back to the structure and change it whenever needed. So, and then we built this bridge, conversation between the mushrooms and humans, as I explained a second ago. So this is a very good example in my mind to show that you have to be very experimental when you're designing things, right? So if we keep doing what we already know, we can move, only incrementally. So, but to take a huge leap in innovation, to come up with new ideas, to be really transformative, we have to experiment, right? So, and then this way, from this perspective, actually, this is, let's say, a good example to illustrate that. And then we can suddenly shift our mind to elsewhere, right? So design is about structures, design is about making things and so on. But at the same time, design is a lot about seeing. So that's why we keep, building bridges between the structures that we make, but also how they really look, right? So there's always the aesthetic side of things, and that's why we're always interested in arts. And we really cannot, remove art from architecture, from design, right? So whatever we do, I think they have to look good. We have to have some sort of delightful moment. We have to have some sort of delightful moment when we look at these, let's say, artifacts of design. And to get there, actually, there are some techniques that you can use, right? So one is just looking into whatever is existent around us and taking parts from them and then reassembling them. So this is a very famous painting. It's the Wave of Kanagawa. And what you can do is you can start isolating the parts, right? The waves and so on. And then you can combine them in a way to create some new designs. And this was a technique that I used while teaching at Rhode Island School of Design. And this is, from one of the students that I had at the time. So turns out that actually we copy a lot. So we look at things and we get inspired by them and we copy what we see. And this is not something bad. This is very natural, right? And we use these terms like biomimicry and so on and so forth, which is revealing, our, let's say, understanding or our operation in copying things. And so that's the second way, to remain transformative. So we have to experiment, but we need to also copy. And it's a good thing to see and copy things because this is how we build things. And the third thing that relates to design is pretty interesting too. So this is a very interesting binary question, right? So I can ask you, okay, is this a duck or a rabbit? And depending on the orientation of the picture, that you can come up with a solution, you can come up with an answer, but there's always the third answer or the fourth one or the fifth one, right? So here what I'm doing is I'm superimposing the image of a crocodile on top of that duck rabbit image to show that actually as designers, we have more opportunities than what we see around, right? So we can have another layer of interpretation, again, maybe experimentally, look into things and see new things. So it turns out that, again, the seeing is another way, another strategy to remain transformative. So these three, if we take these three things and put them together, I think we always have a way to come up with new ideas. And we can again discuss this in different realms, right? So if you look into these two things, what are they? Are they data plots maybe, or are they some printing? Are they some artwork? So we can keep discussing, but essentially, what we are looking at here is this. So what's happening is there's a pen that's attached to the branch of a tree, and it's drawing a painting when the wind blows. So we can interpret this in two different ways. One is that, yes, it's an artwork, drawn by a tree. It's a painting, it's a drawing. But at the same time, we can say that this is a data plot because there's so much information about stiffness of the branch, the strength of the wind, and the location of the tree, right? So all of these three things are related and affecting the outcome of the tree. And if the tree changes, if the location changes, then the painting will eventually change. So we can also discuss this as data, right? And data is very important because nowadays we're all talking about data, and those numbers and colors are always very, very important for us. But then if we pause for a moment and really try to understand what data is. Like, we have so many numbers, what do they really mean? We will realize that depending on the domain that we're working in, or depending on the problem that we're working on, the meaning, the description of data really changes. So in this case, I'm using, for instance, these colors to explain or to indicate the torsion that needs to go into each and every beam for this building to be realized. Although this building looks relatively simple, it's a fairly complicated building in which the elliptical ribs pull back and scale down simultaneously, which create these, interesting connection for the beams that needs to be put in place. So to have a continuous structure, then you would need to give some sort of, torsion to the beams, and these colors are essentially referring to the amount of that torsion that needs to go into the structure. Uh, it turns out that I'm using those colors and numbers to describe a structural, situation, or what happens, what needs to happen to the structure for the building to be realized. So in a way, I'm using these numbers and colors to describe something to you, right? So, and in this respect, we can say, hey, data is something for describing, then I'm using this as a tool for description. And I can suddenly shift from this huge scale, that building, right, which was hundreds of meters long, to a very much smaller, let's say, area, which is your food. And I can say, hey, data can also be something that is found under your foot. And in this case, we can shift our attention to a runner, and then we can put a pressure sensor in his shoe, and then start extracting some numbers and colors from there. So what's happening here is that the runner is running, and simultaneously the pressure is being measured under his foot and the numbers are being collected, right? So then you need to go into those, and with an awareness and knowing that how the pressure sensor really works, and then make this heat map, the data map again, right? So eventually you end up with something like this. And the rest is, okay, what do we do with that then, right? So, okay, we measure the pressure, we have a lot of numbers, we clean the data, we came up with a clean, nice picture that is representing the pressure under the foot. What's happening here is that there's a phenomena that's happening, but we cannot really understand everything simultaneously for the runner, right? So the runner is doing a lot of things. There's a lot of stuff happening with him, but we can only look into a portion of the problem, which is under the foot. So what we are doing is we're splitting the world into parts, right? And in this case, first we are looking into the foot only, and then we are looking at the pressure only, and then we're subdividing the pressure into pieces so we can have an understanding of the, of a greater picture. And then essentially, once we get the information, the idea is then starting to put those parts together, and then we make designs, right? So that's exactly what happens in our mind. It's not that direct though, right? We cannot really go from data to design immediately. So we collect the data, we have to have a method to parse that data, to read that data, and that can be scripting, that can be visual programming, and so on and so forth. And then the colors and shapes appear elsewhere, right? So we give a form to it in 3 dimensions. And once we start mapping some shapes onto the data, then we have, let's say, a design. And we call this algorithmic design, right? So you see a lot of stuff like this. It's technically doable, right? But the question is, which one of these is the right solution is very challenging, right? So you don't really solve the problem when you map a Voronoi shape onto a structure, onto some sort of like data distribution. You have to have a really good reason for that. And it's also very important that whatever we look at, we only partially understand it and partially solve it. So in this case, I'm just representing the high pressure areas in the structure, leaving the rest. And even if you try to attempt to all of it, probably you wouldn't be able to solve the problem 100%. And it's fine, when we're building buildings as well, right? So we can collect a lot of climate data, we can collect a lot of data about the settlement, about the site, and so on. But we can only use so much of it, and we can only respond to so much of it. Anybody who's claiming to respond to 100% of his is not telling the truth, right? So it's not really possible to do such kind of things. With that awareness, you can apply these kind of understandings to products, to buildings, and to any other sort of design that we are working on. So I had a chance to work on this project that you're seeing on the screen, and I'm the designer of that black part in the midsole, and that's a 3D printed part. It's interesting in the way that it's a new sort of part that didn't exist before, and that is made with a new material, and also that is made with a new manufacturing technique, right? So all of these newness is happening simultaneously, right? So lots of ideas and lots of techniques are transforming, if you will, over time. And when you switch the mode of designing and production from, let's say, conventional ways of manufacturing to digital manufacturing and 3D printing, it's lots of change. Okay, a lot of things change. It's not only the part, it's not only the way you design, but it's also how you approach the design. So in this case, if you look at the colorful shoe on the left side, you would see that it has a heel component that has nested parts. Each and every nested parts represented or seen in different colors. They're made of different materials. They fulfill different functions, whereas the one on the right side has one single black part. So what's happening is essentially you're replacing all the function of different nested parts with one single part and embedding all that intelligence into that unibody form, which is the part that you see on the right side, right? So that's the heel component. And if you had a chance to touch this part, you would realize that it's really soft in the middle, and then it would be super rigid on the sidewalls. And the flat faces that you have are used for assembly. So all the parts, all the let's say zones in this part is behaving in a different way. And the one on the left side that you're seeing is the part that I had a chance to design, and you would see that the top surface is looks totally different than the front surface, totally looks than the side surface, right? And beyond those looks, also everything has to function and fulfill a purpose of supporting your foot and hopefully being bouncy and performing in the way that you are expecting it to. Uh, so here we have to talk about the transition from digital to real, right? So it doesn't happen immediately. So you have to develop a method of going from digital to real, right? And this should encompass the designing process, again, testing process, and then the manufacturing process. So the computer thing doesn't necessitate that the perception will be great too, right? So here we are looking into intricate, colorful 3D printed model, which looks super interesting. But then you have to shrink the scale so much to the extent that you can fit into a midsole on the right side. But beyond that technique and beyond the, let's say, the potential to print it, it needs to feel good, right? So how can we really do that is the question. So there are steps of, lots of steps of computation, which is, let's say, you discover a way to make a form, and then morphing and blending, which helps you to identify different purposes, different zones in a shape, and then change your structure depending on that purpose, so your structure can respond to that need, right? And then distribute in the right way and have this seamless model, right? So all of these things need to happen, let's say, on the digital side. And while you're working on this on the digital side, you know that you have to explore, right? So you don't have one single answer at one single moment. You have to diverge, open up, the problem and find different solutions or different let's say instances of design at different moments to have an understanding, build an understanding of what you're really doing. This is nothing new, right? So this is about design space, and it existed for a long time. But by using these tools, parametric design has been picking up in the last 20 years to, explore and understand these ideas. So you make a design space and you kind of see your options. That's the idea. And then you can expand your design space even further. These are some very cool images created with by my colleagues at New Balance, and it is displaying the structures that we looked into, right? And it's only a portion of what we were doing, so we have many more than these. So it's not only that you take one single shape here like gyroid and look into its potential, you also expand your understanding into many different structures, and some of these structures are actually inspired by shell structures that we use in architecture, right? So having that architectural background also helps me understand how a structure really works in this like minuscule scales, right? From buildings to let's say to shoe design. You can kind of reflect some ideas. And eventually what we do is we keep diverging and we create this improvised design space, right? And then we keep making these parts. We make a lot of them, and we test them, and we document them, and we track them, because the idea is once we achieve something, we can just have that as a milestone. But at the same time, if we have to go back to another structure that was not so good for one purpose but was very good for other purpose, we can track that down and go back to it to reuse it or repurpose that structure. So again, this is implying a big shift in, parts are changing, processes are changing, methods are changing, the way we test the parts are changing too, right? And you can apply these ideas to buildings too, because in the past, let's say you weren't using and the amount of simulation that you're using now in, let's say, one of the digital platforms, it wasn't there, so you weren't using it that much. And also the construction, the way of construction is also changing, right? So we are incorporating lots of digital manufacturing into architecture today. Same thing applies to shoe design, same thing applies to product design, and so on and so forth. So for this industrial design projects, the emergent field of design for additive manufacturing is really important. I gave a 2-day workshop in the past 2 days for the conference attendees, and we looked into the techniques and very crucial points of designing these minuscule structures. So if you're interested in looking into this field, please search for design for additive manufacturing. What we essentially are looking into now is, in the past, for different purposes and for different uses, different performances, we would use different type of materials, right? Again, the same thing in architecture and product design. But today, what we can do is we can use the same material, change the shape, right? And then end up creating these metamaterials, which is a new field, again, for at least 3D printing. And it's an expanding field for this purpose. Okay, so what's happening here is, again, there's a transformation, there's a change. And what used to be fully digital, that, the things, the forms, the surfaces, boundary representations that we played in the digital realm, now we are making solid models out of them really fast, and we are 3D printing them. So this is very significantly different than conventional, let's say, manufacturing techniques, because the shapes that we are making are significantly more sophisticated and complicated than what we used to do in the past. And once you start analyzing these shapes that we print, now we're able to, get an understanding, have an understanding of these shapes by testing. And when I say testing, you can have this rigorous, engineering testing methods, but at the same time, you can only, take the very simple route of touching and understanding how something really works. Like touching is a very important for human sensation, and it's a great way to learn. As you see in these pictures, you can immediately understand by just looking at the photographs one side of this structure is super stiff, whereas the other side is, like super smooth, like a brush, right? So you can kind of like bend and twist that portion of the structure. And what we do is we use this understanding to make a lot of parts, and then again consider them as metamaterials that we can compare them to conventional materials that we had. So in this case, we are taking these little shapes which are filled with structures and comparing them to the foams that we used to use in shoes. And it's interesting that at the end of this process, if you use this like mechanical testing, we produce data again. So we started with data, we made parts, we tested the part, and there's data again. So it becomes a cycle, right? In a way. These are the two structures that we used in the two shoes that I mentioned a while ago. The one on the left side is the structure that we used in the heel component. The one on the right is the structure that we used in the forefoot component that I designed. So it doesn't end with the internal structure, right? So especially for the sneaker heads, the way the looks of the shoe is very important as well. So it has to look good. You have to like the shoe when you look at it. Same thing goes for the buildings, right? So when we look at a very appealing, attractive building, it takes its part in the history of construction. Whereas if it is an eyesore, you don't really want to look at that building. And in this case, because the scale is so small for these shoes, you have to go into very small details under 1 millimeters, and then work on these flowy forms. But at the same time, we really enjoy making these visualizations to explain how much effort is going into the making of the shoe, how intricate these forms are, and the variety of the forms that we are using in these shoes are really expensive, right? So it's kind of like really a wide, let's say, they fall in a wide spectrum. Okay, so again, I'm just showing the 3D printed components that we used in these two shoes. So we call this triple cell, if you would like to check this technology. And we partnered with Formlabs, who developed the material for us while developing these shoes. And here I would like to share this short video with you to show the process of the making of the shoe.
The future of additive manufacturing is really the ability to create high-performance parts for athletes, to be able to manufacture on demand, and really be able to customize for the individual athlete's biomechanics.
Yeah, and with additive manufacturing, we believe that we're going to be reducing R&D timelines as well as production timelines. There's going to be on-demand and regional manufacturing that's going to allow us to reduce lead times as well as reduce the amount of shipping of product all around the world.
Triple Cell is our new technology platform created with 3D printing.
When we started this project, we knew we needed a very specific material. It did not exist in the 3D and additive space.
We knew we were going to need a great partner to help us bring this to life.
Yeah, unfortunately, just 4 miles down the road from our Brighton headquarters, we found the right partner, Formlabs.
We've been working on this material with New Balance, and the goal was always to create a disruptive new material that has the extra kick that a specially designed material can get you. We specifically formulated a material that has very high elongation and a lot of energy return.
Unlike foam cells, which are made with chemistry, triple cell is made with computational design and data, which allows us to produce precisely shaped and sized structures.
The real magic of Triple Cell is what our own internal design team brings to the process.
We literally started developing methods that don't really exist for additive manufacturing. And it really enabled us to iterate and reiterate and reprint so many parts. With the foam, we designed a part and make some engravings on the surfaces. Whereas with the 3D printed parts, it's like carving. We designed the volume, like what we take out from the space.
We can adjust in any local region the structure to address different aspects of the foot strike, for example. We can really take a more supportive structure, for example, what's on the rim of this part, and we can blend it with like a more cushioned structure, for example, what's in the core of this part. One day we can really do that on a person-by-person basis and offer a completely unique ride for every individual.
The world is changing. People want custom things made just for them that have higher performance, that can ship overnight. We've been working together with New Balance, figuring out how we can go from a prototype footwear all the way to small batch manufacturing and then all the way to mass manufacturing.
We can take all the output from our pilot manufacturing line right now and take it down only 2 floors from where we're sitting right now and assemble into a full shoe. The ability to turn that quickly is going to be a great advantage in the future.
Triple Cell is really on the leading edge of bringing New Balance domestic manufacturing into the digital age. We've really traditionally been involved in what have been really analog and manual operations, and this is a huge opportunity for us to move into more innovative products that are produced domestically.
Through Triple Cell, we're making huge advancements. We're really going to be able to disrupt the industry not only in performance, but also in athlete customization and speed to market. And one of the things that's truly unique and special for us at New Balance is that we're developing and we're manufacturing these components right here in our own factories and in the United States.
So briefly, here you can see this is my colleague, and we ended up working a lot together with Chris while realizing these shoes. And he's the designer of the the heel component that you saw. And the process took a lot of course, discussions, a lot of learning, a lot of iterations and reiterations of of these shoes and the design parts. And a lot goes in manufacturing side too as well, right? So it's not only designers playing with this and making crazy forms. We learn a lot from our technicians, our engineers, our biomechanical engineers, production managers, and so on and so forth. So it's a huge conversation that involves everybody's infinite amount of effort to kind of like realize these kind of projects. And here you're seeing our manufacturing facilities in which we moved from prototyping to, let's say, production in scale, step by step. Okay, so this is the one of the end products, and it's one of the designs that I'm really lucky to have found the chance to design. So again, what happened is the parts changed, right? So these parts didn't necessarily exist the way they are, as we are seeing in these images in the past. And that is also changing the description of shoes, right? So eventually what's going to happen is, what I'm anticipating is, it's going to be maybe with parts first, but then the whole shoe is going to change. So we are going to move from this very conventional understanding of a shoe to something really crazy. So the shoe becomes a field around your foot. So if you search that, shoe as a field, I had a chance to run this workshop at MIT in which we, challenged these descriptions of shoes and came up with new descriptions of, let's say, what a shoe could be. And the same idea applies to buildings, right? Buildings are made of parts. You put the parts together and the whole emerges. This is a project that I worked on around 2006. I was very excited to be a part of the process. And it was a time when generative design was barely kind of like picking up. So you would only find a, like a narrow application area for these projects. You couldn't, kind of reflect these techniques onto all projects. This is a huge building. You can see, how small the buses are. It's a train station that is spanning 500 meters to 500 meters. So it's a pretty large, let's say, canopy. And it's interesting in the way that the idea was somehow this, flowing, let's say, complex but simple form, right? So it's interesting in the way that our vision creates these images which has no parts, right? So it's in our mind, it's this crazy form. But when we need to realize it, we have to discretize, subdivide into pieces. I talked about this when I talked about the underfoot pressure, right? So it's the same thing, that we go into the problem, we cannot really understand it at once. So we split that problem into parts, and then we combine those parts back together to generate these forms. And again, we can use digital fabrication to realize both, right? So here, whereas we're using some, let's say 3D printing, laser cutting, and so on and so forth to realize this model digitally to represent architectural integrity. Whereas on the other side, we are using a CNC mill to represent our vision of the structure. So these are significantly different two models, which one has no parts, the other one has a lot of parts that are put together. And this was pretty much a design that I worked on at Kohn Pedersen Fox around 2006. And at the time, I was really interested in creating these forms, but at the same time, the second one was experimenting, right? So I was very interested in taking the forms and also working on, let's say, rationalizing these structures to be constructed in an easier way. So what you see here is this is a building, and the design is almost done. So you have to go back to it and, let's say, generate the floor plans in a way that you end up getting this, smoother surface for the building to be constructed in a simpler way. So what I'm doing here is I'm keeping the visual, let's say, expression of the building while I'm simplifying the curvature values of the building. And you can see that on the image on the right side, the colorful from the difference between the let's say, rationalization and post-rationalization of the building. But it doesn't end there, right? So once you see forms like that, that's a very interesting building form. You also want to go, crazy, let's say, make these interesting forms on top of it. So that's the experimentation part. And I had a chance to, let's say, work on that side too. And all these models with the train station as well were exhibited in SIGGRAPH in 2008. And I also had a chance to talk about these processes and write a little, let's say, article about it, and which was published in this book. So if you're interested in reading about the foundational, let's say, ideas about parametric design, this is one of the greatest books in the field by Robert Woodbury, and I had a chance to contribute to it too. What we do, or what we used to do a lot in the past by using these generative tools and design tools, was generating patterns. So essentially what I showed you about the shoes is the same thing. It's a pattern. It's a very sophisticated pattern in 3D. But in the past, or still in architecture, what we do is we make patterns in 2D. And for this project, I was really interested in creating these language of pattern, which can be read by humans, but at the same time by computers. So you can see my hand sketches, right? So I'm trying to come up with this language, which only has, let's say, 10 to 20 different parts, but which are only achieved by using 5 or 6 different parameters. So you would have, panels that are in the front or at the back, and you would have mullions that are tilted right or left. And then, once you convert that idea from visual to, let's say, into a code, then you end up getting something like this. So this is a code that can be read by a machine, right? Because you have all the, information about the panels, but also visually it can be read by a human saying that, oh, okay, this panel is, that type of panel. So I really enjoy building these bridges between the two realms. But at the same time, it is very important for me to explicate and describe these, processes. So what I ended up doing in the past, or what I'm doing now at work, is always getting these pseudocodes prepared, right? So it's not only let's say, the design process that the design that we deal with, but we also deal with the process of making it. So how do we make something is very important, and we have to explain other people that way of making. And here we are showing the logic board of, step by step, what happens where on the generative design side when we're using this tool. And the second thing is I'm switching to a project, but it's very related. It's a pattern project too, and I can jump to it's again like pseudocode, so which is slightly different, which uses different parameters to make these shapes. But what's essential is that computers doesn't always generate satisfactory results. They don't always create what we are looking for, right? So at that moment, you have to empower the designer. You have to give the tools to the designer so the designer can go and change whatever he or she thinks need to be changed. So in this case, you would see this red circle right here, right? So that circle is, let's say, showing, the panel that checks the neighbors and updates itself according to that. So it's an automated process of, self-awareness for the tool that is trying to keep the panels, let's say, slightly different than each other in one single location, so the design doesn't get boring. But does it really solve the problem of, let's say, not having the desired result? Not really. You can still get, like, let's say, undesired results. And then we ended up putting these smaller circles that you see here. And literally, the designer would go and click those little circles to change the rows if he or she wasn't happy with the design. So this is to really reinforce the idea that designer comes first, right? Whatever simulation, whatever tool we use, they create some suggestions for us. The computers create suggestions for us, but not necessarily a full solution for us. So we have to keep a door open to change those designs, because designers keep seeing, right? You would remember that duck, rabbit, crocodile. So in the case of this building, let's say we saw a moment ago, the seeing is like the vision is not really satisfied. So we have to kind of change our mind, change our idea, and change the design. And this is a good question because it relates to the tools that we are using today, right? So we can use generative design tools, but whatever we look is super dynamic. They change all the time. So here we can see, 2 squares or 4 triangles. If you dealt with shape grammars, you would know this problem. So if you're using BIM, and on the BIM side, this either needs to be, 2 squares or 4 triangles, or you have to define whatever it means. So it cannot mean a 5th or 6th thing, right? So we can subdivide this thing or discretize this, these 2 squares this way or this way, which is the 4 triangles, using the idea of shape grammars. And in a way, we realize that the parts can change, right? So I've been talking about this part whole idea. And I keep writing about these too, so you can check my Medium page on that respect. So parts always change, and the holes that we look into are not necessarily made of clear parts, right? So we have to switch between the ideas of parts and ideas of holes, and they have to remain really dynamic for us to be transformative, for us to move to the next thing. And the other thing is, I've been talking a lot about humans and computers, and explain why vision is very important, what computers can and cannot do. So these are also very important. And referring back to shape grammars, humans are very powerful and in the way of seeing these new shapes. And here I'm just showing a trace that I made by hand, which wasn't pre-compiled, predefined by a computer, right? So the pattern at the back, although it's drawn by hand, it's an array, perfect array that's generated by image processing on the computer. But it's me who goes and draws that red, let's say, area. So this is having the will and the power of like seeing new things within, let's say, defined structures. And we can always talk about this in terms of computation too, right? So I can keep seeing, I can keep drawing, but at the same time, I can explain this as a step-by-step procedure that can be, let's say, described in computational terms. The difference is if I hand this to a computer, it probably generates, whatever is predefined before. But here, what I'm doing is, let's say at some moment, I'm switching from tracing the dark areas to tracing edges, right? So that's my decision. And I'm changing my mind and coming up with transformative technique, if you will, exactly, on the way, right? So we have to use this like the power of being human. And again, we talked about seeing, and copying is very important because copying help us build styles. So these are some oil paintings that I work on. And for me, it's always a, let's say, a challenge to generate this kind of, let's say, ambiguous, let's say, textures and colors and so on by computers, because everything you make kind of like ends up being somehow flat. So I had this questions, okay, if I like, how can I replicate the style, that I'm having on the oil painting side? So as I was painting, I was taking the photographs of the paintings, and you would see that, there's some sort of a language. It's not 100% there yet. They're not really matching 100%, but there's a recurring this, technique that I'm using with the knife, painting knife, and it's helping me build this, let's say, style. But what it really is not that clear. So what I did is I collected these, I put these images together, and then I fed them into a machine learning algorithm, and this was the outcome. So what we see here is they are really reminiscent of the paintings that I did, right? We see paintings, we see colors. They're somehow merging and blending, and they're more streamlined than the paintings themselves. But at the same time, it's an extension of my work, right? So I don't evaluate these on the same level with my paintings, but they're helping me expand my understanding to the next level. And what do I do with these images? So first I analyze them, I look at them, and interestingly, sometimes you see some outcomes. Oh, where is this thing coming from, right? So there's like a circular object there. And it turns out that, within the collection, I had one single image which had these speckles, right? So it's interesting that when you're working with machine learning, the outcome, you can guess what's going to come out, but there are always surprises, right? So I like that surprise part. And this kind of taught me that, okay, the data set is really important. And even if you have, let's say, one single, painting that has these weird features, they may appear back in the painting this way, right? So it's a good learning process. And then the other thing is, everything comes, let's say, washed out from this process. So you have to go back to it and sharpen it and so on and so forth. So what I'm doing is I started with oil paintings. I took the photographs, I ran a machine learning algorithm, and it helped me produce these interesting images. And then I ended up making clouds, right? So I was like, okay, where is this coming from? So this is exactly using, let's say, an image like that, right? So I'm using this and I'm transforming into, let's say, a meshing algorithm this time, and bitmap processing, then this thing emerges. So this is very inspiring for me because it doesn't also end there. I can still move on to the next step. But in a way, this is very similar to looking at the clouds and finding shapes in them, right? So I'm doing vice versa. I'm looking at the shapes and making clouds out of them. So this is again, being on the move. This is again moving from one idea to the other one, because by using these images, I ended up making these forms. So they are very kind of architectural, right? And I was very surprised to see that in myself, because I was coming from, end of architecture, product design, oil painting, and then suddenly something architectural really emerged out of these by using machine learning, by using 3D modeling techniques and meshing algorithms and so on and so forth. So in a way, this is again having this momentum to remain transformative and move between ideas and remain creative. So I just happen to say it: remain creative, remain transformative, keep changing things, right? So, and these were pretty much the tools to do that: experiment, copy, and see. And we can talk about, okay, so these are in the let's say abstract side, but you can also apply this in your business. Okay, you may already have a business, or maybe you will have a business in the future, or for your projects, right? So this is about innovation, and you can use these ideas to build this framework for yourself. So this is a framework about innovation. I call this how much innovation can you afford? And it's pretty much for showing how you can define your design problems, how you can work on finding solutions for them, and how your trajectory affects the results, right? So the idea is your problem might be very speculative, and your solution might be very speculative, right? So this is kind of like pushing the boundaries of design. Or you may have a very grounded problem, like, okay, where do I put, the living room in my layout kind of thing. And then your solution might be really grounded. Okay, I did this already 5 times in the past and it somehow works. So I'll just keep doing the same thing, right? So those are the grounded, safe, let's say, solutions. But the newness, the true innovation comes from pushing the boundaries, right? So you set the problem really speculative and your solution is really speculative too, right? So that's the North Star usually in design. When we hear something new, when we hear something striking that is, wow, how did they do that? That is the North Star that I'm talking about, right? And to get there, you have to keep, let's say, you have to let go what you know a little bit, right? So I did this many times, but let me try another idea. This is how you should approach that. And then you achieve the North Star. Because if you're pushing the boundaries of innovation, this is how you should do it. Because once you get there, you can then trickle down, from the edges and let's say, come up with a more subtle solution. You cannot really create a subtle solution and then go to North Star. That's very hard to do. If you push the boundaries, then it would be easier to simplify, your design and come up with, let's say, a grounded solution. And but there are also kind of, let's say, limitations, right? And one is that if you're going speculative, you have to deal with a lot of ambiguities and challenges. Whereas if you're grounded, things are more concrete and easier to handle. And that would probably pretty much be your mindset. And again, I just explained this, but the outcome is very important. And if we want to change, create big change, paradigm shifts, you have to kind of like go for the low star. And if you have, a project that you want to remain low risk, if you have a business that you cannot risk things and so on, you have to kind of like come up with, grounded problems and solutions. And again, you can find this article online too, and you can find pretty much this innovation framework as well. Okay, so all of these ideas existed forever for humans. I would just claim that these ideas as old as as old as the history of humankind, and I'm just gonna take you back in time and to Renaissance, right? So this is an engraving by Albert Dürer, and he made it around the time he said, "What is beautiful? I do not know." If you look at the engraving, so he is depicting himself here. It's the doppelganger of Albert Dürer sitting among these tools of measurement and among tools of computation, right? So you can see a scale for measuring the weight. You can see a compass. You can see hammer. You can see tools of making and so on and so forth. Magic numbers, square, and so on. But what is he or what is she doing? Just sitting indifferently, right? Like not touching anything. And there's somebody's holding a banner saying melancholia. So this for me in my mind is referring to the fact that we can have the tools, we can have the power of computation, but if we don't create meaning, which is quote unquote beauty, then we are not doing much. And in this case, probably at the pinnacle of Renaissance, right? So Albert Dürer has all these tools of depiction, measurement, computation, and so on and so forth for the time, but he has the idea of beauty. He is looking for the next thing. He's looking for the new idea. He's trying to remain transformative, right? So he wants to move to the next step. And this critical view is the only thing that can help him to do so. So the tools without our critical view wouldn't mean much. That's what I'm trying to say. And beyond me, a lot of people say that as well. So we can look into this article from Forbes, which was published last year, and Forbes has been publishing this for the last 3 to 4 years. And this is the list of skills that you need to succeed in future. So look at those skills. Are there anything about computation? Are there anything directly about AI and so on? They're not necessarily really there. So what you look and see are the qualities about being human. So critical thinking, I mentioned previous slide, which is number 2, and then creativity is something that I kept talking about, and I talked about, people management and coordinating relates to the diagram that I showed, which is about innovation and so on and so forth. So all these skills are about being human and trying to achieve and create beauty and meaning, as we saw in the previous slide. And to recap everything, computation is great. Trying to remain transformative is wonderful. And we are in a digital age. We are in a data-driven age, and we're using, lots of processors and computation power to do so. But at the same time, what we need to use essentially is the insight that we have, as I tried to illustrate in this, Photoshopped logo here. So with that, I would like to thank you all, and I will be happy to take any questions. Please try to visit, me on the online platform seen here, so we can keep sharing and learning from each other. Thank you again. Thank you, SIGraDi 2020, for having me as a keynote speaker.